Thank you. Thanks a lot, Alyssa. So I'm Maneesh Agrawala, and I think that all of us can agree that, that one of the best ways to communicate quantitative information is to visualize it in the form of a chart or a graph. And in the last 300 years or so, since these forms were invented, they've become pretty ubiquitous. We see them all the time in things like scientific papers, in textbooks, in newspaper articles and magazines and financial reports and on and on and on and on. They're all over the place. And one of the things that we've been thinking a lot about is what makes these kinds of visualizations so effective. So let's see if this is going to work. Okay. So this is work from William Playfair. In 1786, Playfair, an English economist, published the Commercial and Political Atlas. And this compared the economics of England to the rest of the world. It was the first published use of line charts and bar charts. Now, these images here are from the third edition of the book, and this was published in 1801. And one of the things that I find really interesting about these images is that except for the typeface, these look remarkably similar to modern line charts and bar charts. They're very, very similar. And so one question here is, why do these charts look so modern? And so let's look at this example from Playfair in particular. It shows the balance of trade between England and North America. And in case you can't see it, I know it's a little small, the x-axis shows time. So over here on the left, it's 1700. Over here on the right, it's 1800. So it's a century of years. And on the y-axis, they're showing the amount of money or value that was transferred either from England to North America, that's the line of exports that we see here in red, or value imported from North America to England. That's the line of imports here in yellow. And so in the 1700s, in the early 1700s, the early part of the century, we see that the balance of trade is really in favor of North America. And this pink region shows just how much more is being imported from North America than exported. In the last half of the century, we see that the balance of trade is strongly in favor of England. And these greenish regions kind of represent how strong the balance has shifted. And we also see that in the mid-1770s, there's this interesting dip in the amount of trade. And this is, of course, the Revolutionary War. And so trade almost came to a standstill. You see there's still a little bit of it going on, but it declined pretty sharply. And then the chart also shows that right after the war, trade picked right back up, and England returned to having trade heavily in their favor. Okay? All of that is really clear to see from this chart. Lots and lots of data presented all at once. So, well-designed charts like these are really great for people, like you and me, to understand and see the data. We see the data in context. We see a lot of it at once. It helps us make sense of the data and understand it. And I think this is the reason that these kinds of charts and graphs have endured for so long. But for machines like these robots, it's difficult to understand these images. And so a big part of the problem here is that the charts are represented as pixels. And the machine really has no way to access the underlying data. And that, I think, is a problem. Now, here's another chart. This is a visualization of NIH's research budget per death spent on various diseases in 2005. And we, people, can see that AIDS takes up most of the budget. It's much higher than any other disease. But we can't really tell, even if we look closely, whether NIH spends more on diabetes or on Alzheimer's. the areas or angles of those two pie slices are very, very similar, and it's hard to tell the difference. So while this visualization still communicates the data to people, it might not be the most effective design. And these kinds of poorly designed visualizations can be found all over the place. Here are a few examples. And if you go to various websites, you will find more collections of bad visualizations. This is one of my favorites, this 3D pie chart from Fox News. It's from the 2012 presidential campaign. And as I think many of you have noticed, for some reason the pie slices don't add up to 100%. But going back to our NIH example here, if we had access to some of the underlying data, we could fix some of the problems of this pie chart. For example, we could label the slices perhaps with the amounts that they represent, or perhaps redesign the chart completely, transform it into a bar chart, for example, where it might be easier to read off the differences in values. But again, here again, the pixels really make it difficult for people to accurately get access to the data and to manipulate the chart. I have no way of reforming this chart if all I have are the pixels. So what we've seen is that pixels are not a good representation for charts and graphs. They make it difficult for both the people and the machines to work with the underlying data and information. And the goal of some of our work has been to deconstruct these kinds of bitmaps of charts into a representation that enables redesign, reuse, and revitalization of the charts. So that raises a question. What is a good representation for charts and graphs? Now, fortunately, visualization researchers have addressed this problem. And what I'd like to do at this point is walk you through one of the most important ideas, I think, to have emerged from the visualization community over the last 30 to 40 years. In fact, it starts with thinking about how to represent data. And this really happened in the 1940s. Stevens was a Harvard psychologist, and he developed a theory for the scales of measurement. We can think of these as different types of data, and he defined 4 of them. So first is nominal data. This consists of categories or labels. Categories of fruit are one example. So you can label a fruit as an apple, an orange, a pear, a banana. And you can compare these values. You can test for equality and inequality. All right? But that's the only way you can compare them. Next is ordered or ordinal data, and this has a ranking or an ordering on the data. Grades of meat are one example. I was recently told that we phased out grades of meat in the US, but in Canada they still have grades. I think the ranking is still important. How many people know about grades of meat? Do we still have this in the US? Yeah? Yes? No? Okay, it doesn't matter. There's an ordering, there's no distance between them. So you can't tell, there's no way to assess the distance between grade A and grade AA, right? So you can compare things in terms of their order. Next is quantitative data, and there are really 2 forms of quantitative data. One is interval data, and here we have an arbitrary 0 location. So we can't directly compare values, we can only compare differences between values. And the second type of quantitative data is ratio data. Here, there's a fixed 0 location. It has semantic meaning, and so you can directly compare values. For the purposes of visualization, we usually combine these last 2 categories, and we think of the 3 main data types as nominal, ordinal, and quantitative. Okay. Next, we need to think about how to represent images. And in the 1960s, French cartographer Jacques Bertin really laid the foundation for thinking about charts in his classic book, The Semiology of Graphics. And he thought of charts as composed of 2 things: a set of marks, such as points, lines, and areas, and visual variables or attributes of the marks. These control the appearance of the marks and encode the data. So, for example, we can use the position of a mark to encode two values, one for the X position, one for the Y position, and so on. So we can think of a chart then as a set of marks with mappings between the data and the visual variables or visual attributes of the marks. And a bar chart is a set of line marks. Each bar is a line. And data is mapped to the size or length of a line. A scatter plot consists of point marks with one data field mapped to X position, another mapped to Y position. We can, of course, add additional visual variables. So here we've added color. This is a colored scatter plot. We've added a third data dimension. And so this scatter plot is now showing 3 dimensions of the data. And of course, we can also map to size. So now we have a 4-dimensional scatter plot with a different data field mapped to each one of these attributes. Now, I'm going to come back in a moment to tell you how we might deconstruct a chart into this representation. But I want to continue a bit with Bertin's ideas because I think they're really important. So, and the one takeaway that I want you to remember from this talk is that we can really think of a chart as a collection of mappings from data to the visual attributes of the marks. Okay, so here's a bit more from Bertin. He also considered the way that people perceive the visual variables in the marks. And so here we have a set of 3 point marks. The pluses are little representations of points. And we can see that the points are easily distinguishable from one another. And in this case, they're collinear. We can also compare the distances between them. So we see that BC is twice as long as AB. And Bertin used this kind of reasoning to suggest that position is really good for encoding quantitative data. Okay, so where we have differences in distances between the data, this kind of encoding using position is really good. He also explained that gray level or gray value is perceived as ordered. So given several patches of gray values, we can easily order them based on whether they're closer to black or white. But it turns out, as you can see in this example, that very fine distinctions between gray values are much harder for people to see. If you look at this example in here, points that are very close by in this continuous ramp, it's hard to distinguish them visually. And so what this means together is that gray value is good for encoding ordered data. It's not so good for encoding quantitative data. And then finally with hue, we think of hue as unordered. There's no natural ordering to hue. And so this is really best for encoding nominal data. Okay? We do learn an ordering on hues, but that's a learned thing, like the rainbow ordering. So Bertin ranked all of these visual variables in terms of how well he thought they could represent the 3 types of data. And what he found is that position and size are good for all 3 data types, nominal, ordinal, and quantitative. Value we saw is really best for nominal and ordinal, not so good for quantitative data, and so on. So that's how you can read off this table. And I should point out that Bertin mostly conjectured this effectiveness table based on his own experiences constructing charts and graphs. And in fact, in later experiments on graphical perception, most of these rankings were verified. In fact, here's an example of one of these experiments. This is an experiment done by Cleveland and McGill, where they asked people which of the 2 pie slices marked with dots is bigger, or which of the 2 bars marked with dots is bigger, and also how much bigger the bigger one was than the smaller one. Okay? And they were trying to figure out how accurately people could extract values encoded using either the angle of the pie slice or the position of the tops of the bars. As you might imagine, here are the results. So what they found is that angle encodings are significantly less accurate than position encodings for these bar charts. All right? And here, based on a number of such experiments, researchers have ranked the effectiveness of the different visual variables, and these really match the conjectured effectiveness that Bertrand set up. This, I should point out, is for quantitative data. There are similar rankings for ordinal and nominal data. So going back to the Playfair chart, we can identify the underlying representation. We can figure out the data, the marks and the mappings. If we had access to this mapping-based representation, we would have a very nice representation for manipulating the charts. Another important thing when designing these kinds of charts is to map the most important data to the most perceptually effective visual variables. So here we see that it's using the mark type of lines, and year is mapped to position because year is very important. Year is along the x-axis. Exports are along the y position. It's let's say, the second most important data field in this data set. And so those two together form the line of exports. If we're willing to have multiple lines, then we can also map imports to y position, and we get this yellow line of imports. And so that's the way you can think about constructing this kind of chart and making a very effective chart, because it's based on the perceptual effectiveness of the visual variables. Now, we've been developing a set of techniques to try and recover the structure, the data, the marks, and the mappings from a pixel-based representation, an image of a chart. And so we'd like to take an input like this pie chart that's pixels, and recover this structure, the data, marks, and mappings. And the reason we want to do this is because it facilitates redesign. So I can start with a set of marks and mappings, areas for the mark, and mappings, budget goes to angle, and change the mark to lines and the budget going to the length of the line, and I turn it into a bar chart, okay? And so the mapping-based representation is very, very powerful. I can very quickly and easily do this change and get a completely different visual chart. And in this case, I can perhaps see a little more clearly that NIH spent a bit more on Alzheimer's than on diabetes. So I want to briefly touch on what we do. Our approach is to take a bitmap image, like this bar chart over here. We run it through a classifier and determine the chart type. So a bar chart, a pie chart, a scatter plot, and so on. And then we've developed a set of chart-specific techniques to take the input bar chart, analyze where the foreground data encoding rectangles are in this case, and then figure out, based on an analysis of the axes, the value associated with each one of these bars. And that allows us to pull out the data, and implicitly, we also have the mappings from the marks, from the data to the marks, the association between them. And of course, we can do a similar thing for pie charts. And these techniques are using a variety of machine learning and image processing and computer vision techniques. So I should mention that our techniques are not 100% accurate, but our classification, at least, is pretty close. The number to look at is this binary SVM. It runs at 96% accuracy, so that's pretty good. The extraction of the marks and the data, that's not quite as good. And what we're seeing here is that we get between 60 and 80% accuracy at extracting the marks, depending on chart type, and then between 40 and 56% on extracting the data. Now, I should point out that these are conservative numbers, and these are we're only reporting here cases in which we exactly correctly extracted all of the marks and all of the data. And there are many, many charts in which we miss on one or two marks and so on. In any case, there's more work to be done here, but this is a reasonable starting point. And when we do extract this representation, we're able to do redesign, like I showed you earlier. And this is all done simply by manipulating the mappings. Okay. Here's another example. So we've reordered the bars from largest to smallest. And we've also adjusted the baseline. In the original chart, the baseline didn't start at 0, which can be very confusing and lead to errors in interpretation. Here, we've set the baseline to start at 0. And then here's a very different style of chart. This is a dot plot, which gives a clear and compact display of the distribution of the data. And this is all done simply by manipulating the mappings. Now, recently, we've been investigating how to extract the data marks and mappings from a chart constructed programmatically using D3. D3 is, I think, pretty much the de facto tool for creating interactive visualizations on the web today. There are hundreds and thousands of these visualizations widely available. And so in this case, by analyzing the code, we can exactly recover the data and the marks and explicitly recover the mappings between them. And the nice thing here is that we can start with a bar chart like this, do our deconstruction to get the marks and the mappings and the data, and then by simply deleting 2 of the mappings, we're able to produce a very different looking chart, this dot plot. Okay? So again, this mapping-based representation is very, very powerful. Now, even more recently, we've started to build reusable style templates. So here on the left are 4 different D3 visualizations that we've pulled off the web, and we've converted them into this mapping-based representation that serves as a style template, and now we can pour new data into these templates and generate visualizations for the new data set in any one of these styles. And we don't have to stop there. Here we started with a new data set, but we can also take existing visualizations, deconstruct them, and then pour them into the templates, and we get the same same data visualized in many, many different styles. And this is all done automatically. Okay, so the last thing I want to leave you with is some work that we've done on revitalizing visualizations. And this is going a little bit beyond redesign. We're really thinking about how to bring static charts and graphs to life and enable interactions that might support different kinds of chart reading. So just like Curtis showed earlier, the work on the paper of the future, you could imagine these kinds of interactive charts that I'll show you in a second in a paper of the future. So the thing that we're adding are what we call graphical overlays. These are visual elements that are designed to support and facilitate the perceptual and cognitive processes involved in chart reading. And what I'd like to do is just show you a demo of what we've done. So let me shift over to this. Okay, so here up top is a static chart. We scraped this from the web, and it was just a set of pixels. We deconstructed it, and now we can add in reference structures. So I'll press that, and we add in these divisions, and these divisions can help you read off the values of the bars. They help you project the end of the bar back onto the axis and read off the value. And I can change the number of divisions like this. I can make it an underlay to give it less prominence. And I can also make it interactive. So here, I can just place my reference lines at the end of the bar to help me for that one bar. We can also do highlighting. So here I have interactive highlights. When I hover over a bar, it desaturates everything else so that I can focus on it and read it more accurately, and so on. Okay, here, these are redundant encodings. So the value of the bar is written next to it, right? And I can now read the value directly. And then finally, summary statistics. So here we've added a line that represents the mean of all of the values. We can do the max, of course, and the median. So these kinds of additional overlays can really support different kinds of readings of the data. And remember, we started from pixels, so we can take existing visualizations and add these onto them. So there are three things that I want to leave you with, and that I hope you'll remember from this talk. First, we should think of charts as a collection of mappings between data and visual variables of the marks. And the most effective visualizations map important data to perceptually effective visual attributes or variables. Second, we can use image processing techniques and also code processing techniques to recover this representation from images and programmatic charts. And finally, this reconstructed representation really allows for many different types of redesign, reuse, and revitalization. More importantly than all three of these takeaways even, is that a good representation really supports new ways of thinking about data. And this is something that artists and art thinks about a lot. They think about different kinds of representations of their work. And representation is also at the heart of science. And so I think this is a deep point of connection between science and art, really thinking about the representation that you're using and how that representation changes your thinking about the work. All right, I'd like to thank the people that made this work possible. The two people pictured here were the students that did a lot of the heavy lifting that I showed you. For more information about any of these projects, please check out our website. Thanks a lot.